arc is generic if it intersects transversely every simple geodesic. Now, doesn't seem that it would exist, but you remember that this result of Biermann series, which I mentioned yesterday, says that there are very few simple geodesics. They only form a set of transverse dimension, their union only forms a set of transverse dimension 1. So there are so few of them that actually any arc can be approximated by a generic arc. For instance, almost every geodesic arc, you take one at random, then it will be generic, it will be set. Well, if you have an arc like this, and it's transverse to all the geodesic laminations, then each geodesic lamination gives each measure of geodesic laminations gives a measure on that arc. So, and then what you can do is that you can topologize this set by the weak star topology or on the set of measures on this arc. Well, what that means is that you need to say that a sequence of measured laminations converge to another measured lamination if and only if for every generic arc K and every continuous function defined on that arc, then the integral of phi with respect to the transverse measure with respect to the measure alpha L converges to the integral with respect to the transverse measure of alpha. If you think of it, that's a very natural topology. I'm not an analyst, I don't know. Someone, I hardly know the general definition of weak star either. And okay, then you have a similar result which says that if you put that topology, then the ones coming from a simple closed curve, okay, when you have a simple closed curve, associated to the geodesic lamination with the transverse measure, and then you can multiply the transverse measure by whatever number you want, and the result says that the ones you obtain that way are dense. So I said it's like this idea of going from the set of simple closed curves to the space of measured lamination. You have to think of it as analogous to the process for which you go from Zn to Rn. And really, if you're a topologist, the reason why you should be interested in that is really to understand a little bit what happens as you go to infinity in that set. And that's, if you think about why you want to consider real numbers if you study Zn, very often it's because you want to go to infinity in Zn. Well, I don't know. People might disagree with this statement, but that's my view of the thing. And here it's the same idea. Okay. But really, what the topology is finding?
You said that the space of lamination is totally discontinuous. And you said we're going to topology of the measured lamination.
Yes.
Is it at this level, is it already obvious that we can place in arcs?
What is this space here? Yes, that next slide, it's a manifold.
Yeah, but is it obvious that it contains curves?
Which set?
This new set, ML.
ML. No, I don't think it's. Total brains, yes. Yeah, no, that's it. No, you have to. No, I don't think so. I mean, no, the first time you see the definition, you might think it's a counter set too. I mean, there is a problem with the word obvious, but for people like me, certainly it would not be obvious. Okay, but actually, the lagging point in this case is that, okay, we're going to see it, okay, if you look at this last slide, it's a topological manifold. So it's like it's homomorphic to some Rn, to see that thing. However, it's not a smooth, so it's not a differentiable manifold. And that's really why I started getting interested in this weird object. Okay, because it's a piecewise linear manifold. So first, what Thorson showed that Thorson answered Etienne's question in the sense that he computed the topology of that tree. And the idea is that the first idea, which is relatively natural, is that if you look at enough generic arcs, then it's completely determine the measure lamination. That's quite reasonable. Right? So you take, and you can find n arcs, so that if you evaluate if you integrate this arc to effect the transverse measure, they give you a map of the space of measure laminations to Rn, one copy for each arc, and the fact that it's an embedding is natural. But what's more surprising is that you can determine the image, and that the image is a piecewise linear submanifold of Rn. Now, what's piecewise linear, I have to remind you a little bit, that the map is piecewise linear, where there are many definitions, but one way to do that is to say that you can decompose the domain as a union of palatably closed polyhedra, and where the map is linear. And this one is confused with the okay, and so piecewise linear submanifold, that's something where you have piecewise linear charts which make it look like RP in Rn. So that you take the standard definition of manifold, but you replace submanifold, but you replace differentiable by piecewise linear. And piecewise linear homomorphism. Okay. And then in addition, if you take an additional generic arc K, then you can express this number here, alpha of K, namely the integral of the measure of that arc in terms of the other ones. And not only you can express it, actually it's a fairly explicit formula, which you can make explicit, and it's also piecewise linear. So what that says is that if you take two sets of arcs like this, then the change of chart is also going to be piecewise linear. So because of that, what you get is a structure of a piecewise linear submanifold on this space here. So you have to understand what that means. That means that this is a topological space, and you have charts which model that space over Rn for some dimension n, and that the change of charts are piecewise linear and not differentiable, or differentiable manifold. And then something which is not too important here is that person was also able to completely determine the topology of this space, and it's just some Rn where n is this thing here, 3 times the characteristic of the surface minus the number of curves. I mean, the formula is not important. It's not even important. For the talks, this is not. What? Try and track. I mean, you are the close lemma. I mean, you approximate geodesics by thinking short cost rules. And you construct explicit coordinates in that. Okay, now, piecewise linear manifolds, they've been around in topology for a long time. Right? It's a nice way to interpolate between topological manifolds and differentiable manifolds. I should say one thing, that you can show that, okay, you will think that it's a founding method, that this is wrong. But actually, you can show by hand that you cannot put on this space a differentiable structure for which, on this space here, you have a natural action of a group, and there's a group of diffeomorphism on the surface. So any structure, any structure I want to consider here would be invariant under that. And you can show that there is no differentiable structure on this space which would be preserved by the action of the group of diffeomorphism. In other words, that if you cannot conjugate, well, exactly that, yes. So really, the piecewise linear context is the only one which is available to you. And the problem is that, on the other hand, people like to do calculus, and calculus for piecewise linear manifolds, on the head of myself, calculus on piecewise linear manifold, that's really the Lloyd. So I'm going to take an example, which is that everything you do for simple closed curves, you can often extend it to measured laminations. Of course, in particular, many functions have this property. And one of them is the length function. I mean, it's a simple one, so I'm going to choose this one as a guide. Okay? So the length function, if you have a closed curve and a hyperbolic metric, then you can consider the length of the closed curve. But if you want it to be invariant on deformation, what you do, you take all possible closed curves which are homotopy to that curve, you take the length of those and you take the infinite. But in practice what that means is that I told you that this curve is homotopy to a unique closed relation, you take the length of that one. Okay. And so it's an observation of Thurston that you can extend it to a continuous function. Which is linear in the sense that if you multiply the transverse measure by a number 8, then you multiply the length by the same number. Okay, and let me show you how you do that. It's a simple idea. You have to choose the lamination bad, but you can take 500 mm transverse arcs so that we split the leaf into compact leaves. Okay, you can always do that by the current. Okay? So now you have compact arcs. Well, for each arc, you can measure its length, and then you integrate the length with respect to the transverse measure, and then you take the sum over all the boxes. So it's a natural idea. You see again, the key point is that you take the length of this arc and you integrate with respect to the transverse measure. And then the continuity, once you understand that, if you vary the measured lamination, what the length of this arc varies continuously, and it varies, the measure varies continuously too, so the length should vary continuously. That's not a proof, right? That's the idea. So it's continuous. But the question is it differentiable? And and so the problem is that what's the differential? Now you remember that when you have a differentiable manifold, the differential is a map or a tangent map. It's a map from the tangent space of the manifold. Now you go into R, so it goes into R. And so the differential should be a map like this. But the problem is that this is not a differentiable manifold, it's piecewise linear. So what's the tangent space on a piecewise linear manifold? You know, like a polyhedron, what's the tangent space at a vertex? Well, there is a notion of tangent vector. Just take the usual definition for differentiable manifold and then you translate it to the piecewise linear context. So I don't know, you take standard textbook differential geometry, and you see the definition of tangent vector they use there. So there are various ways of defining tangent vectors on manifold. I don't think you can use derivations here, right? Okay, my favorite way of thinking of a tangent vector is as something which is tangent to, as an equivalence class of curves. You say that to another point, to define the vector, you define an equivalence class of curves where you say that two curves are equivalent if you have two curves at the point here, and you say that they are equivalent if they have the same tangent vector. That's what you're aiming at. And so what you say that you consider their images under a chart, and you see that they are equivalent if their image here is tangent. And the point is that actually, the key point is that this property is invariant of the chart if the change of chart is differentiable. But actually, it's also invariant of the chart if the change of chart is piecewise linear. So actually, this standard definition of tangent vectors in differentiable manifold extends to the piecewise linear context. Without changing anything, the only thing you lose is that a piecewise linear map is not linear. And so, in particular, the space of tangent vectors, which you can always define in this way, that's not a vector space. That's not necessarily a vector space. It doesn't even have a multiplication by -1. Because look, if you have curves here which are tangent, which were having the same tangent vector in one direction and in the other one, well, when you do the change of chart, it could look like this. Then it's not being aligned anymore. So you don't even have that nice operation. You do have the operation of multiplication by positive numbers, however. So that's a little inconvenient, but actually topologists have known how to work with these things for a long time. However, I'm trying to do some analysis here. I'm trying to differentiate. And so, how can I do that? And you know, when you're stuck on a problem, what you do is that you do examples. And so, let's do a simple example by going back to, by taking one which is associated to an interval exchange map. So you remember, I told you yesterday that, about interval exchange maps and how they give rise to geodesic laminations. And also, I told you that the Lebesgue measure on the interval gives you a transverse measure of a geodesic lamination. So if you just take this one, which is one of these things, I never thought of this on the rotation of the circle. Now, I want to be here and talk to you about but this one is the rotation of the circle. I agree with you guys. But, so it's a simple one. It's an interval exchange map on two intervals where just you have one of length 1 and one of length t, and then you send this one here and this one there. And then when you construct the suspension with the freeway, remember, well, you take a rectangle going from here to there, that gives you this fat rectangle here, and you have this teeny one here, or with t going this way corresponding to the other one. Okay, and the surface is a function for us. Well, it's something nice. And so what I'm going to do is I'm going to let t vary from 0 to epsilon. So I have a one parameter family of measured geodesic lamination, and what I have is a curve in this space. And alpha t, that defines the curve. And we can actually show that this is piecewise linear curve, or piecewise linear structure. And so, and then, well, we just draw pictures. Now, I told you that for a generic interval exchange map, it's going to have infinity many views. That's annoying. I mean, I don't know how to counter sets. However, there is something nice, which is that if you let t equal 1 over n, I'm trying to have t goes to 0, so go to 0, so it's not a bad idea. Then it's simple because actually you just have all the orbits are parallel. And so, actually, for t equal 1 over n, what you get, the geodesic lamination is just a single closed geodesic. Here is for n equals 4. So, number of 1/4, that's just a simple geodesic which goes once around the horn here, and then n times this way, and then goes back, go back here. On the other hand, the transverse measure is t. So, in this case, t corresponds to 1 over n. So the transverse measure is the counting measure. And then you evaluate, let's take this arc here on the picture. So the intersection of this arc with the geodesic lamination, that's n points here. Well, you call them x. So for later, you put all the odd ones on one side and the even ones on this side. It's going to be nicer. Yeah? So you have n points like this. And the transverse measure is you evaluate the function at these endpoints, take the sum, it's a finite sum, yeah? It's a Dirac measure. And then you divide by 1 over n. And that corresponds to the t factor. Okay, now you just sit down on the description of the matrix here, of the Lebesgue measure, and so on. That's what you get. That's relatively simple. And if you let n tend to infinity, when the picture converges to this here, namely, you have this geodesic here, which it turns n times. When you feel that n goes to infinity, this geodesic is going to start turning infinitely many times, and in the limit what you get is one closed geodesic, and then a spiral like this. So that's what we saw yesterday already. And then, if you look at the intersection with my arc here, I get infinitely many points which accumulate on the point of intersection with the closed geodesic. Okay. Now, remember what I'm trying to do. I'm trying to find I want to find an interpretation for this derivative here. I mean, I have a curve, t gives alpha of t, and I want the tangent vector. And the tangent vector formulae is d over dt of alpha t at t equals 0. And d over t plus, because I only want the right derivative. Well, so then you go back to the definition of the derivative. The derivative, so now, this is a family, these are a family of measures. So I'm going to plug in a function phi, defined for my arc k. So I'm going to take the derivative, I want to take the derivative of alpha t here with respect to the time t. And the definition of the derivative, well, that's alpha t of phi minus alpha t of 0 divided by t. Okay, that's calculus. And then since I don't understand all the t's, at this point I'm just going to look at the ones where t equal 1 over n. So, actually, this is more important. Okay now? So I want the derivative. So alpha of t minus alpha of 0 divided by t. Well, for t equal 1 over n, I can do this. N at the top. And then I go back to the definition of this, which is here, namely it's a Dirac measure. So I evaluate the function at these endpoints. And I have a 1 over n, which cancels that with this one. And then here I evaluate the function at this point, that was for t equals 0. And that n here gives me an n here. So I have infinity. I mean, when n goes to infinity, this goes to infinity because we have many, many more points. But this goes to infinity too. And infinity minus infinity, well, that's not 0 like my calculus could speak, but it's, so that's not 0, that's just interesting. So you play a little bit and you incorporate these in here, so you get this. And then, look, you're taking the sum from 1 to n of the value of the function here times the value of that bottom point there, times the value here. And my calculus students, they do know right away that if you let n go to infinity, you get this here. And the sum of 1 to n is 1 to infinity, and just you plug in n equal infinity there too. And the point is that if you use this labeling, which is nice, to order your points, at level n you have x1, x2, x3, x4, depending on n here. Well, when you go to infinity, you still have x1, x2, x3, x4, x5, and 6. And there is a way where the x3 point here is going to converge to the x3 point here. So at least formally, but we're not trying to prove anything here, but formally, we find this here. That's a physicist proof. But we've seen this guy before. Yesterday, there was an example of transverse distribution. You remember that? That's the example I gave yesterday. Yesterday, I gave an example like this, where you take the sum of the infinite sum of the difference in value of phi between the value at the least point and the value at all the other points. Well, that's how I got started in this whole thing, just by staring at this example and drawing lots of pictures and so on. No, so then the next theorem, which is that, okay, so that's only a very heuristic argument, but then you can justify it. Now, more generally, if you take any curve, if you take any curve in the space of measured lamination, and there any one parameter family of curves, and which has a tangent vector in the, for the piecewise linear structure, then for every under continuous function defined on a generic arc, well, you have a number associated to each. You consider the integral of phi with respect to alpha t, and then you can take the derivative, and the derivative exists, and it also defines a regular continuous for the Helder distribution for the norm of the Helder continuous function. So it defines a Helder distribution on that arc here. And then, in addition, as the transverse arc ranges over all generic arcs, then you can show that the support of this transverse distribution gives me a geodesic lamination, which usually is larger than the one the support of the measured lamination alpha 0. In this case, for det equals 0, I just have a closed geodesic, but when I come to the derivative, its support is a closed geodesic plus additional leaves, like this. Okay. So the whole point here is that going from the combinatorics of this piecewise linear structure, you end up with an analytic object that gives an interpretation of a tangent vector as a geodesic lamination with a transverse Helder distribution. You go from the topology to the analysis, which is what's important here. And then there is a converse, which is not. Conversely, if you, well, you don't need to read everything here. I'm going to advise these people. The idea is that, conversely, if you are given a point at in the space of measured lamination, and if you're given a measured lamination, and you're given something which looks like a tangent vector at that point, and then you're given a geodesic lamination which is larger than the support of that, and with the transverse Helder distribution, then you can characterize what if that geodesic with a transverse distribution will correspond to a tangent vector to the lamination. The conditions briefly are: the first one says that the support of for the Helder distribution should not cross the support of alpha 0, and then the other two are a certain positivity condition. I don't want to. It's not important. It's just positive. It's just some positivity condition. And in particular, so that gives you a way to understand this tangent space in an analytic way, where starting from a measured lamination, so with a small support here, alpha 0, well, the tangent vector you obtain it by adding this geodesic, by taking a geodesic lamination which is larger, by adding some isolated leaves, some minimal things. So what condition 2 says is that if you add a minimal sublamination, then it has to be disjoint from everything else. And on the other hand, if you add an isolated leaf, then as a corollary, it has to be its ends have to be asymptotic to the support of the measured lamination to start with. And in this, and now if you fix a geodesic lamination and you consider all possible transverse Helder distribution which can occur in this way, then they form a linear face in the space, in the tangent space, and which is contributed only if the lamination is chain vectorant. Well, either you know that, either you don't. It's not too important. Okay. Forget that this remark I will talk about. Okay. so the setup here
The
is
idea
that
is that we have a green point, and you preserve the green point by adding a small coefficient on the red side. Is that
yes,
the idea?
yes, yes, yes. You're going to add, yeah, you're going to end up with a small, if it is in a, you're going to have, if you see small, but the topology here is going to change.
And then a small coefficient, so it's smaller.
Okay, now, so what I did is to transform this piecewise linear tangent vector, which is something very combinatorial, into something analytic. And so, how can we use this? Well, I will say something about the proof here. It's formally, you can get, I will have another one. The previous slide saying that every tangent vector gives you a geodesic lamination with a Helmholtz distribution, with a transverse Helmholtz distribution. Proving that formally it's an easy code. You can start with the gap formula, for instance, and then you do formal computation, it works fine. It's a little more tricky to justify. You need some broad estimates, which are not completely trivial, but you work hard, and once you've worked hard enough, then you're done. You don't have to think anymore. So for instance, let me go back to the idea of the length function. The length function was defined on the space of measure lamination. And so you want the differential of that. And you remember, I already said that the length function, you define it by taking the geodesic lamination, you cut it into small pieces in transverse arcs, you look at the length of each arc, and you integrate with the transverse measure. Well, if I want to compute the differential of the length, well, what I need is a curve which is tangent to that tangent vector, to the tangent vector. Okay? So I take a tangent vector, I take a curve which is tangent to this. Look at it. I didn't say that. Okay. You take a family T in alpha T, which is with derivative of this vector, and I want to take the derivative of the length. Well, derivative of the length, that's derivative of that integral, I said. Well, everything is so natural at this point that the derivative of the length is just the length of the derivative. I mean, this makes sense. This integral makes sense even for the geodesic lamination, the transverse Helmholtz distribution, because you know the length of this arc is actually a Helmholtz. It's actually a Lipschitz function of the arc. So you can integrate it with respect to the transverse Helmholtz distribution that sits at the normal. And everything is so natural that when you take the limit on both sides, you get that. And it's linear and so on. So actually, the derivative of the length of this length function, that's just the length function defined on the space of geodesic lamination is transverse Helmholtz distribution. So it's very natural in this context. Okay. So, as a preparation for next time, so that's exactly the kind of results I was aiming at when I started this program. And everything started just by looking at the example I gave you. The question here is the following. If you're a topologist, you don't like to have to fix a hyperbolic metric. I mean, what happens if, when I take a metric like this to study the space of single closed curves, what happens if I take a different one? Okay? Well, then nothing changes. I mean, this theory is metric independent. And the reason, so, if I take another metric, then there is a standard fact about the negatively curved metric, is that for, if I have a metric, a geodesic for the metric M, then there is, I can associate to it in a unique way and geodesic for the metric M prime. That's the key word here is that something which is geodesic for the metric M is going to be quasi-geodesic for the metric M prime. Okay? So, so there is a unique M prime geodesic which is going to stay at bounded distance of G. Okay. So in this way, I give you a natural correspondence between geodesic here and geodesic there. Now, if you take two geodesics like this, which do not cross, and these ones are not really crossed either, and therefore you get a natural correspondence between M geodesic laminations and geodesic lamination for the other metric. Okay? So the theory of geodesic lamination, it's metric independent. Okay? There are other ways of defining this, which make it a little more natural. You never use the word metric anywhere. Now, the transverse measure, actually, that intuitively, it's a measure which is locally defined in the space of leaves of the geodesic. Well, again, because of the correspondence, that gives you a translation between transverse measures for an M geodesic lamination and a transverse measure for the M prime geodesic lamination. So these measured lamination places also are the same. And then if you think a little bit about it, you can also show that the correspondence preserves the piecewise linear metric. You have to work a little more. But this space here, as a piecewise linear manifold, this is metric independent. So that's why really the topologists are really interested in that. And the important addendum is that this correspondence also is not only it's continuous, but it's Hunter-like continuous. So that's something which is actually fairly familiar to the people who do these kind of things. For whatever metric you put on the space of geodesics, well, whatever distance you put on that space, whatever natural distance, then it respects this marking is Hunter continuous, and the inverse is also Hunter continuous. And so, what that shows you is that when I take geodesic lamination with a Hunter distribution, transverse distribution, it's also metric independent. So actually, this whole theory, which was topological to begin with, is still topological at this point. Namely that this does not depend on the choice of the metric. Now, the analysts don't care about these kind of things, but the topologists do care, because we don't want the original problem studying deformation classes of simple closed curve. That is very metric independent. So you don't want a theory which at the end would depend on the metric. But everything I did here, you can do it without possibly in place. Okay, and then, so I think that's it for today. And then tomorrow, I'm going to, so here I chose a sample, the length function as an example. Tomorrow, I will choose, there are many more applications of these things, but I will choose one, and talking about three-dimensional hyperbolic geometry, and how you can apply these techniques to that context. Okay.